Hey, Kool-aid Krew, what's crack-a-lackin'? Hope everybody's doing good. We are going to kind of just jump into it. Somebody give me a 5 for 5, and we'll get into this. Yeah, guys, we got an incoming solar storm, and yeah, so that's what you get right there. This is NOAA, and what you're seeing here is an in little spiral. This is their forecast. Green line represents Earth. This thing was fired off, right around the turn of the day, 12th to the 13th. You can see it right there. This is a side cut. Sun, Earth, Sun, Earth. So, it fires off there. This is 2 days historic data that we already have. So that's exactly correct. 5-day forecast. This was done yesterday, so it hasn't been updated since then. But as you see, right here about the 16th, at any time right now, UTC, that could be any time as I'm speaking to you. This thing can start to hit. And it kind of looks like it might be, because I'm looking at some data, and I was, could be just now starting. So we're going to kind of get into it. But yeah, so we are 5 for 5. Okay, cool. No sound issues this time, I guess. Also, guys, this was on the 14th. There was a blast up here. Also want to bring your guys' attention to this. You guys see this line right here? That is actually the tail of the comet. Okay, so let me first off turn my turn my volume off on my phone so y'all don't get a reverb or an echo. So you can see it right here. Now this is a coronagraph. This satellite is from our viewpoint. It's right there. It's right out in front of Earth, always looking at the sun. So it stays in that position. It's 1,000,000 miles closer to the sun than what we are. So we get kind of almost like an hour warning when things are fired at us from the sun, because it'll hit this satellite first. There's a few reasons why they have that there, but I'm not going to go into that right now. But all you really need to know, that is from our perspective. So this is actually called an observatory, SOHO Observatory. It's a satellite observatory. It's got multiple imagers on it, multiple data collectors, all kinds of equipment on this satellite. Now, this one is sitting in a position that has no protection from Earth's magnetic field. So anything that hits it is definitely getting raw space weather, okay? With that being said, that should also, tell you guys the resilience of these things. They can be out there if they're built right, okay? This thing gets hit all the time. So stereo A and stereo B is still there too. Just we don't get data from this one anymore. But we do get data from stereo A. It used to be over here and give us a side view. It was awesome when it was out there because we had a partial backside view, and we could also get a better idea of when things fired off the sun, what direction they were coming, because essentially what it did is not only did it give it a viewpoint from right in front of us, okay, but it gave us a side view. It's as if you were looking at this, but actually from space. That's what the camera would be looking at. Because here's the sun, if you just kind of pull back to about Earth's orbit, like right here, that's where this satellite was at. Or this is a top-down view, so it was even kind of back here for a long time. So we had a really good idea about what was going on here when we get things fired off our direction. We had a much better and easier way to see what direction they were going when we had these satellites to help us. But this satellite, stereo A and B, have outlived their lifespan. So they brought them back closer to us. Now, I'm not sure if they're going to send them back out. My guess is probably not. If they do, good. If not, I'm not counting on it. So that's just kind of where I'm at with that. But right now, current Aurora, I do want to bring this to your guys' attention. Not really much going on at the present time. But we're going to take a look. Now, this was last night. You see how we kind of had a little burst right there? We almost got into a geomagnetic storm last night. And let me show you here. You can see it right here. We measured geomagnetic activity with the KP index. It's just an index that they've come up with and been able to measure geomagnetic activity. So with that being said, we got to a 4. KP of 5 is what starts storm level. G1 is the lowest form of a geomagnetic storm. Okay, now typically we don't see a whole lot from those things. We do get an increase in Aurora. That's one of the biggest things we can always point to. But our baseline for X-ray flux, or X-ray production, is being produced by the sunspots. Okay? Notice how our base is down here close to the bottom of the C class range. Almost in the B range at some levels here. Okay? What that means is we don't have a whole lot of X-rays being produced at the moment. And the reason why, and I will show it to you. I thought I hit that play button there. But you can see these are the sunspots. Every time you see a little bright spot here, that is the sun producing X-ray. That's what's happening. That's what a flare is. Okay? A flare and a CME are different. A CME, which was what that was, there was a flare involved too at first, but then the CME came after, and the CME is a plasma eruption. In other words, highly charged particles erupt off the sun. You can have a flare without a CME, and you can have a CME without a flare. That was all space weather changed dramatically with the Carrington event, 1859. That's when they were really, they were able to see, pretty much for the first time, to be able to differentiate, hey, those two things are different. Because up until that point, they thought they were just one event. But that's just simply not the case. Now, as time went on, we use ham radios a lot now too. So that, things started to become more and more evident for the difference of those two as time went on. Because when we get these X-ray bursts, they're here in 8 minutes. Okay? So when you look at the sun, you're seeing what the sun looked like 8 minutes ago. Okay? So that's just how long it takes light to get here. Now, when you're talking about the other, CMEs, it takes time. It has mass. So it's typically between 2 to 5 days. It just depends on how powerful the blast is. That's as simple as that. But when we get X-ray blast, in other words, a flare, it will cause radio propagation to degrade, right? And so what you're going to see, this is the D region. Okay, this is the region of our atmosphere. And you see how when you get that bullseye signature, that's a flare hitting. And that was not a very strong one, but it was strong enough. When you see this, this is most likely at least an M class. It takes about an M class flare in order to excite our atmosphere enough to mess with radio propagation. Okay? That's kind of the floor, the threshold that we use. Now, it's going to be mainly on the day side of the planet, which unlike a CME hits, it affects globally because it comes in a different way. Okay? It comes in, it gets drawn in to our system at the poles. So it kind of, yes, the day side gets hit a little harder at first because that's just simply the direction it's coming from. But it does filter around to the backside. Okay, so everything gets hit. So I often don't say that, and I probably should more often, but I don't. But that is what happens. This is a coronal hole. This is the surface of the sun. This is not a hole in the sun. What you're seeing is a hole in the sun's atmosphere. That's called the corona. The surface of the sun is actually colder than the atmosphere. So with that being said, that's why we see it darker here on this imaging. This is from one of the GOES satellites. Almost everybody knows what the GOES satellites are because those are the same system of satellites that we put up there for our local weather. Seeing satellite imaging for weather purposes. Not space weather, but typical weather on the planet. Okay? Rain, all that stuff. Hurricanes, tornadoes. But yeah, so this is the same kind of, it's being done by the same kind of satellites. They're in a low Earth orbit, so they're closer to us. They are inside the protection of our magnetic field most of the time. Unless we get hit real hard with a geomagnetic storm, a blast from the sun, it could compress things enough that the satellites are actually outside our protection for a short amount of time. And that's not good for these satellites. They'll go into safe mode. We've lost satellites because of it before. Starlink lost, I can't remember how many of them. It was over 20 of them during a launch during a G1 storm. And then I can't remember the other company that's been launching satellites too. A week later, during another really low-level storm, a G1, same thing happened to that. So, it makes you wonder. They've launched in much worse conditions before and didn't have those issues. So, what's changed? I don't know. Was it just a mistake at the time? I honestly just don't know. But yeah, so I'll just say that. Okay. Now this is the HP. This is the same indice, right? It's the same. It's measuring the same thing, geomagnetic activity. But this is the KP. These are 3-hour plots, averages. These are 30 minutes, so we get more real time. And as you can see, we kind of been bumping around here close to 4, which is, it's getting substantial enough. Yeah, we need to pay attention to it. We want some geomagnetic activity, guys. We can't just have none. If we had none, then we're susceptible to cosmic rays and other things like that. I've said multiple times in the past, the sun helps protect us from the sun. We have to have a certain amount of stuff, and we have to have the good balance that we're searching for, and usually that's right around a 2, I would say, if you had to pick a number on the KP here. So, we don't want some big massive, level 10 or KP 9 plus or whatever we're going to go here with, right? Some big, world-changing event. But we also don't want to have 0. If we're at 0 for multiple days, they will issue a cosmic ray alert. And that what that will mean is that people that are flying, cabin crew, people that are pregnant, they will be warned against flying high latitude up here close to the poles. Because, like I said before, stuff is coming in easier on the poles because of magnetics. And this is why I really hammer this home. South Pole, same thing, guys. Okay? So, cabin crew, now if you're pregnant, they don't want you up here doing this stuff. It's not so distant past here, guys. They realized that doing x-ray to a unborn child is very, very dangerous for the unborn child. It can really mess them up. So, when we hammer these points home, we're doing it for a reason. It's not just because we just want to say something, right? But sometimes that's kind of how it feels, but that's just not what's going on. But this is LASCO C3. This right here is the same viewpoint as here. Okay, this is zoomed in, and this is zoomed out. It's on the same satellite. It's just a different angle. Well, same angle, but just zoomed out. So we get a wider field of view here. So this is, again, see this arm right here? That's actually there on the imager. It's holding this disc. So that's another way I can show you, hey, look, it's a physical disc. Why do I talk about this disc? Well, when we get stuff that fires off the sun, we don't really know if it's coming right at us or going right off the back because we can't see behind this disc. It's that simple. This white circle here is actually the surface of the sun, trying to represent that. This is here to try to cover up the majority of the corona because that's where a lot of the light is. And these cameras don't like light in that kind of a fashion because it just overexposes and we get nothing but a big white blur. Okay? So that's why that happens. But because we don't have a really good side view anymore, we oftentimes are left to wonder, are these things coming at us or going right off the back? Because they're going to look exactly the same from this satellite. So what's our options? Well, we got a lot of other options. We can go, there's SOLO. There's actually a satellite on the back that's collecting data. Okay? That's there. I'm pretty sure it has some, maybe some extreme ultraviolet imagers. I'm not really sure if it has really good imagers on it or not. I have to look into that. I really don't know. But we do have SDO. Now, again, this is in low Earth orbit. It's in geosynchronistic orbit, which means it stays over the same part of our planet. But it always keeps its eye on the sun. Okay? Which inherently will make it have an eclipse season twice a year. So the Earth will pass between the satellite and the sun. Very briefly, it's usually like a week or two. And it's not all day. It's just like an hour or two. So we do lose data on this satellite during those times. But like I said, guys, we got GOES. Same thing. It's basically from the same point of view. Okay? So we have other things we can go look at. So when we get a blast and we don't know if it's going right off the back or not, because what we're looking for here, guys, is a halo signature. Energy coming around the whole disk. If it's doing that like very, very symmetrical, it looks like a halo. That's why they call it that, a halo eruption. So what that means is exactly what I just said. It's either coming right at us or going off the back. And again, how do we know? Well, then we look at the time of the blast. And then we come here, and we can, if we can find it on the front of the sun here, then we know it's coming at us. We know, we at least know that it was on this side facing us. That's how we know these things. Okay? Hopefully I explained that good enough for you guys. I don't want to like run way out there with you, but I think sometimes that needs explained. I haven't done it like that in a minute, so I figured I would do that for anybody that's kind of new here. Been getting some good amount of new viewers. Thank you guys. I really do appreciate it. Thank you to all my channel members too. Anybody gifting memberships, you guys are awesome, awesome, awesome. If you guys could give me a roll call in here. And I'll keep moving. I want to see where you, just the region. I don't want to know exactly where you're at. I just like to know. And it does help everybody else in there kind of get to know you too. But yeah. Let's do this. Now, this is the Aurora dashboard. Okay, one of the main things we can look at is Aurora. That will point us directly to a solar storm. If we're getting hit geomagnetically, we're going to have increased Aurora every time. Now, is it going to be massive? Well, it just depends on how strong it is. You're going to hear people talk about the Aurora oval. Notice that this is not centered on the North Pole. Why is that? Well, we're talking about magnetics here. So we're not looking for the barber pole where Santa Claus lives, right? That's geographic North Pole. We're looking for a magnetic north. So it's going to kind of be right here where my cursor is, not exact, but it's going to kind of center around magnetic north, and it's going to have an oval because it's moving from one direction to the other. So it's kind of blowing in one direction, right? And the tilt of our planet depends on what season we're in, right? So that matters too. And wherever everything matters. You have to know where you're at, latitudinal and everything else. Longitudinal, all of that matters, guys. So when you're trying to figure out exactly what you're looking at. But this is the Aurora oval, and this is their forecast for tonight. They're saying a KP of 4. If we get into geomagnetic storming, it's going to be a KP of 5 at least. Okay? That would be G1 storm. Now, this is the red line. These are just ballpark type of things here, guys. They don't stick exactly to this. This is a model trying to give you some sort of idea. That's all that's really for. But we can look at the actual what has happened, which is what I just showed you a minute ago. And that's the North Pole, and this is the South Pole. Now remember, this is over here at NOAA Space Weather Prediction Center. Anybody can come over here. It's paid for by our tax dollars. Everybody can access this. Okay? So if you scroll down to any NOAA Space Weather site, it's going to have this. Every tool that I show you is here. Dashboards are here. So the main one I show you guys is a Space Weather Enthusiast. That's this one right here. Okay? It's going to put most of your space weather stuff that's significant to that in a broad sense right here on the dashboard for you. But also, it'll do it for the Aurora, right? And this is what's mainly for Aurora. So that's what we're looking at. Now, not to leave our friends down, out here in the south southern hemisphere, but Australia gets southern lights, guys. New Zealand, multiple places, Indonesia. We see those kinds of things during big storms also. Australia sees these Aurora too. It's not just a northern hemisphere thing. So that's just what I'll say. Hey, Kristen, good to see you. Okay, so let me see where everybody's from here real quick. Pennsylvania, the Purple Princess. Accent Nacho, I know where you're from. Canuck, a.k.a. Heather Joyce here. Utah, Brian Knight. Old viewer, baby. I'm old too, man. Western PA, excellent explanation, Mark. Well, thank you, Jan. I appreciate that. I need to hear that sometimes, guys. I'm human too, I always get the negative stuff, in the comment section. Everybody does. It's not like a big deal or anything to me. I've learned to deal with it, but I am human, and my mood and how I feel about things and how confident I am is affected by what's said to me. I'm just like everybody else here. But I do deal with it. But I will say this. I get so many more positive comments that lifts me up. I'll get one good positive comment that'll erase 95 of the other negative stuff every time. You guys are awesome. Okay, David Lowe, Southwest Saskatchewan, baby. TNAZ, baby. What's up, AZ in the hizzy? All right. The Great Pumpkin, North Southwest Australia. There you go. Hey, I shouted you out there. Hey, Scrappy Cat. Good to see you. See here, think here. Or see here, think. Hi there, Niagara. Love that. Hey, Ron's in the house. Chattanooga, baby. Hilly, what's up? Chardy, it looks like the sun could burst in half. Is that a probability? Texas, Oklahoma? No, the sun ain't going to bust in half, I promise you. If it does, we won't know it. Because we're going to be gone just as soon as it does. I'll tell you that. Hey, Miss, hope you're feeling good, girl. Eastern Washington, baby. Kristen Kruger's in the house. All right, let me get back to it here, guys. And thank you guys for all the gifted memberships you guys continually do. You guys just really do. I'm humbled every time. Leah's in the house. Think I seen her in here for a second. You're from the Milky Way galaxy? I kind of seen that flying by. Hey, Evolution Studios. Yeah, guys, go over and check out his channel. He's got some really good views. Ripper was going to come on tonight, but he had some family obligations. We may be trying to get Rip Crow Readiness in here tomorrow to show you guys the Comet live. That's kind of what we're trying to do here. If I can go on around this time tomorrow, Ripper's out there on the West Coast, and he'll be in, if he's got good weather, he'll be able to show us the Comet live. So, which is very cool. Hey, Idaho Mike, good to see you. All right, now, let's go here. I do want to show you the Helio viewer here. And again, this is just a view of our sun. I'm going to give you the latest imaging here. And I show you guys this for one reason. To give you an opportunity to kind of size it up, right? So when I say we have a sunspot, you know, you really have no idea how big it is unless I do something like this for you. I can tell you all day long it's 500 kilometers long, right? But do you really have a good understanding what that is? I don't think any of us really do unless you do something like I'm doing right here. This is Earth scale, and you can kind of take the Earth and put it right inside that sunspot. Okay, that's how big these things are, and that's a small one. That's not a very big sunspot. You know, we've had sunspots 10, 15 Earth wide, guys. So, I mean, they're big. And I know they don't look big from the perspective we get to see them from the satellite views, but they truly are. There's something to behold if you really sit back and think about what you're looking at. That is just simply the case. Okay? So, anyway, this is the Aurora forecast. So, yeah, we could get hit at any time with this CME. Now, the CME was fired back off on, again, between the 12th and 13th. So if we kind of come back over here and look at this satellite again, we're going to go back to the 12th, all right? And we'll watch, that's stereo A. So we only get a few hours off of stereo A, by the way. So let's go here. Now, so let me pause it, and I'm going to hit start here. Right. I'm guessing that one there is probably the one that hit us. It's going to be hitting us, okay? And I went over this with you guys yesterday. I do think that this is probably the most likely candidate here. I guess it could be the one that started on the 13th. Let's see here. Well, I tell you what we'll do. Let's do this. Let's run this back to the 13th. Where was that CME? See, the CME's already left the sun here. So this had to happen like right around noon on the 12th. The eruption. See how it's just now coming off? So most likely, guys, that is the CME that's going to be hitting us. Right there. Now, yeah. I guess it could have been that one. I guess it could have been one that fired off like on the turn of the day on the 12th. It's a possibility. Like kind of that one right there. That's a possibility. I'm not sure, but regardless, one of those is coming at us, okay? And this is the most recent imaging from SDO. This is the 94 angstrom. I can show you a different color. And when I say color, it's another angstrom of light. It's a specific gas that they look at. So when they look at specific gases, we get a different viewpoint, right? It gives us more detail in a certain area. The 94 angstrom here, sorry about that, guys. I had to take a drink. My mouth was dry. The 94 angstrom here gives us a pretty good idea of where the flaring's happening, okay? And we also see, if you watch over here, you'll see some plasma leave during this eruption over here. It's getting ready to happen. Right there. See that? So that is plasma leaving. Now, that's not coming at us. That's definitely going the other way. I guess we could catch a side glance from that, but I don't think it's forecasted to do that. So if I take you back here and I just change the wavelength of light that we're looking at, you're going to get a total different view. So we're going to look at the 304, and this is ionized helium. This is really good for seeing filaments, which are magnetic ropes on the surface, or in the corona, I should say. You see this big long one right here? Look at this thing. And that one there, guys, that's the one that I said, is going to miss us, right? So if this one over here had erupted when it was over here, we'd be having a different conversation. Because that there seemed to be like it was pretty intense. And I'm going to pause it like right here and show you what I'm talking about. Let's just get to it here. Okay, look at that thing, guys. Look at that. That's impressive. It really truly is. I'm not just saying that. That's impressive to me because I've been watching these things forever, right? Let me do this so we can get a better idea. Now, these are magnetic connection lines on the sun. What you're seeing here is it's the highly charged particles moving from one area to another on this line. When they break and they snap off, that's a CME. So if you look at that, it doesn't even look like it left. Okay? Because it didn't break. You see this? So I don't know that a whole lot of that left the sun. And if I had to guess, I would say not a whole lot did. Now, if we looked at the 94, we can definitely see that some did, but not a whole lot did, guys. I mean, look at that. That thing is towering. Now, remember I had that Earth thing, the Earth scale there, right? This thing. If you were to, like, size that up, look at that. Okay? Let's go in just a little closer here. That's too far. But anyway, you guys get what I'm saying here, right? So if you kind of size it up in your brain here, just kind of with your eyes a little bit, well, I'll tell you what, let me back this off a little. We'll kind of try to match those up, which is probably going to be about right there. That's probably going to be about the same size. Yeah, see? So you see how small the Earth is? You can kind of just rotate that over to here, and you see how big that is? Isn't that crazy? Oh, thank you, Aaron. Get their memberships, baby. Who got them? Somebody tell him thanks. Somebody tell him thanks. In there, whoever got those, tell him thanks. You're awesome, brother, for real. You guys really do. You guys bless me so much. It's not even, I just don't even know what to say sometimes. So, thank you. Truly, thank you. But anyway, the Earth is here, right? So if you could kind of just picture what I just showed you here and kind of transfer that over in your mind, I might even be able to, I probably should back that off just a little bit more. Yeah, it's probably more close, right? Yeah. See how close that is in size? But so that, if you could kind of take this and put it right there, that's huge. So, yeah, and I do that for one reason, to give you guys an idea of how big these things actually are. We just simply can't understand it very well unless we do stuff like that. But anyway, so let me show you this big long filament. This is a big long one. They're not all this long, guys. Typically, they're kind of like this one. Okay? But this one here is really, really big. Okay? I mean, it's on the backside. It's actually connected on the backside here, like right there. So this is a significant one. You can see the particles moving on it. Watch. you'll see the charged particles is moving across it. That's why you see it moving, like right there. There's that blast. Now you're going to see another one here. Do you see that little surge? See that? How it lit up right there? Okay, that was, what time was that? Yeah. So, yeah. And then we had another eruption right there. That's a crackling flare. This sunspot, I've been keeping my eye on it because it is becoming hyperactive. What that means is you're seeing that crackling like a strobe firework, right? And so that means it's continually getting reconnection events. So you're getting positive and negative reconnecting, and when that happens, it causes flares. Now, right now, these are small. It's not going to affect us in such a big way. Hey, Stephanie, good to see you. Tristan's in the house. J Poss, what's up? So anyway, yeah. So that's what's happening with that. Now, I'm keeping my eye on this because it is directly related with this filament. If this thing here was to like really destabilize, it's going to cause this filament to rip off. And that's a lot of high dense material that could be coming our way. A filament is one of the most dense CMEs that you're going to experience. That's just been about what I've been able to observe myself. And I'm sure it's there in the data also. But yeah, so we're going to keep our eye on that one for future and see what happens here. But I do want to show you this also. This is the Discover data. We talk about the BZ, right? The BZ, we look for -6. That's this red line. Again, guys, you can go, this is over here at Space Weather Prediction Center, guys. You can get to this. All these things are in my description box, too. The links are there for them, if you want to check them out. I highly encourage you to. Don't believe a word that's coming out of my mouth. Go look at it for yourself. And, you know, you guys are smarter than what you think you are. And the only reason why I say that is because I get emails every day saying, I can't understand this stuff on my own. Thank you for, you know, doing that. Yes, that's why I'm here. But don't underestimate yourself. Please. I don't have any higher education here, guys. At all in this. This is just something I've picked up on my own. And I trust people that do have higher education. Like Dr. Tamitha Scove and Dr. Tony Phillips over at spaceweather.com. And multiple other people. These people have doctorates in this field. So go check those channels out also. Dr. Tamitha Scove, I always 100%. But anyway, what we're seeing here, guys, is what I call popcorn. Now, a data point is just that on this graph. It's a point. It's a dot. So just like your TV puts a series of dots so you can see an image, similar things are happening here. So when conditions aren't fluctuating, they're really close to one another, you'll see like a solid line form. Kind of like this black line you're seeing here with the BT. Right? But when things start to move, and we start to get hit with things, we see this popcorn start to happen. We start to see conditions just greatly fluctuating in a larger term here. A lot more movement, right? So we're seeing that with the BZ right now. Now, when that's happening with our BZ, that can really, well, I'll just say this. It can really put us in an unstable position. And if we do get hit during something like this, we'll tend to go into geomagnetic storming quicker. And it could be just a little bit stronger than what we were expecting. Nothing, you know, excessive or anything, but that could affect it. So we need this -6, and basically what that is it's the magnetic positioning and orientation. And I'm not going to go into some big detailed explanation on that, but just know we look for -6. So if you come over here and you're scrolling, you can see the -6 in that box. Okay, -6, -7. They'll highlight it here in purple or lavender, whatever your display is showing you. But then we look at density and speed and temperature, right? And nothing's really crazy out of the ordinary right now, other than things are popcorn right now. Things are fluctuating. So, and always come over here and look at your range of what they're showing you here. Because on most days on this density one, you'll come over here, it'll say 0 here on the bottom and 10 at the top, not 100. So when it shows you 100, that's saying that we're getting conditions above 10. Okay? So they have to change that because of that reason. So we get you know, it's probably right in here where it kind of went over the, well, up here's one. What is that one right there? It was like, what, 16? Yeah. So that's why that they changed that for this particular data run here. But just know that. Always look over here, guys. Okay? Make sure you're looking at the range. Because one time you'll look at it and it'll look like it's all crazy high and getting ready to smack you across the face. But it's really not, because all they've done is change this. It's still the same stuff you just looked at 5 minutes ago. They just changed the range. So you have to make sure you're paying attention to that. Now, what I do want to do is this. I was going to show you guys some Aurora photography and stuff tonight that you guys sent in. I may hold off until tomorrow, okay? And the reason being is because if Rip is able to come on tomorrow, I want to show you guys a bunch of your guys' pictures all at once, okay? And thank you guys for sending those in. I really hope you guys do continue to do that. I'm going to show all of them that I possibly can. But just make sure you say I can use it in the email, okay? If I need your account name and tell me I can use it. If you don't do that, I can't show it. And, you know, for obvious reasons. Okay. So, guys, this is spaceweather.com. This is Dr. Tony Phillips. We're under a geomagnetic storm watch or warning, whatever you want to call it there. When we're inside 12 hours of an expected solar storm, I call it a warning because it's pretty much imminent. It's going to happen, at least by their forecasting. Now, a watch would be longer than 24 hours, in my opinion. I'm not sure exactly. I don't think there's any kind of official thing there, but that's just how I do it. But we're expecting this at any time, guys. Now, remember, we're using UTC time, which is the time over in England, okay? So the scientific world uses that because they have to. If we all used our local time zones, could you imagine how complicated that would get, trying to talk to somebody over in Germany or Australia about, hey, what time's the comet supposed to be there? When are we supposed to go look for it? You know what I mean? Any kind of mathematic formula would get all jacked up because of it. But this is the comet. Check this out. Whose picture is this? Let's see here. La Palma, James, let's see here. Nick James of the British Astronomical Association photographed this one. Check that out. Ain't that cool? So, here's the comet. This is called the anti-tail. And it only happens when the comet actually crosses our plane in relation to the sun. Okay? So, if you take the ecliptic, which is what we're talking about here, the equator of the sun, and it stretches out the equator in a very thin line infinitely, that's called the ecliptic. So if somebody says, hey, this comet's above the ecliptic, basically they're saying in relation to the sun and where you're at, it is that comet would be north of the ecliptic. Okay, it's above the ecliptic. Same thing when we say south, below the ecliptic. It's just something we have to have there to be able to understand and give ourselves an understanding of location. Because we have to have some sort of perspective of what we're talking about. If not, we're completely lost. We have to know where home's at, right? Which is why you also see these satellites will do calibration rolls. They have to go into and do that. If they don't do that, we don't know what home is for the satellite. So I could tell it to go left, and it's going to go right. You know what I mean? If we don't know where home's at. So that's kind of what we do with that. So right now, guys, when this is crossing, basically, it's not really the ecliptic, okay, in this instance. But if you were to stretch out from our equator, right, to the sun's equator, whatever that plane is, when that comet crosses down through there on that plane, we will see an anti-tail. In other words, the tail of the comet will appear to point at the sun. It's because of it's a light scattering effect from our perspective from the dust of the comet. Okay? It's called an anti-tail. I know it's hard to kind of wrap your brain around it. I've tried to explain it 3 or 4 times this past week, and I know that I'm confusing people when I do it. So I don't want to confuse people, but please go read on that a little bit. Come here to Dr. Tony Phillips. He'll show you what we're talking about here. But what I can do is I can take you guys back here, and we will, let's see here. Yep, this is exactly what I wanted. This is our inner solar system, okay? This is a model. I've shown you guys this before. This will actually help me show you guys that the whole anti-tail thing again too. I probably should have just went straight here. That was kind of crazy. I should have done that. Anyway, this is the comet. This is the Earth. Okay? When that comet is between us right here, okay, that's when we get that anti-tail. Between us and the sun, when it's crossing that line, right? You see how the plane is kind of tilted here and here and everywhere? And that's why it's different for every planet. And actually, it's different probably a little bit from your latitude. Okay, wherever you're standing at latitude on our planet. Because that's going to change your perspective a little bit. But for what we're talking about, it's not going to change it enough to really matter. In what we're talking about here. Because this anti-tail kind of fades in and then fades back out. Because as it gets closer, we get more dust around that plane. And then as it gets away, we get less dust. Right? So the brightness will increase and then decrease again. So, anyway, just want to make sure you guys understand that. So, this is the path of the comet. Right? So, if I zoom in here and I look, top down, I'll zoom back out a little bit. This is Earth, right? And this is the sun. Here's the comet. So it's actually, it comes real close to the same distance away from the sun as Mercury is. So if I tilt this down, you see what's happening here? That's why this is so important to show you guys. It's hard to show people 3-dimensional things unless you have a 3-dimensional model, which this is not. This is 2-dimensional. But you can kind of get what I'm saying when I'm talking about this. There's something called the celestial sphere also. That's what we use when we're calculating for field rotation. When we get those star trails in the sky, that's because of field rotation. Those stars aren't moving. We're the ones moving. We're rotating. So we have to understand how much we're rotating per our latitude. Our latitude matters, guys. Big time. So if I'm standing here on the equator, the amount of field rotation I'm going to see is going to be a lot more than what you're going to see if you're standing in Canada. So you're not going to see as much roll or as much spinning for star trails and everything else that we talk about with field rotation. We have to figure out our parallactic angle. That's pretty much what you're trying to do there. And the celestial sphere actually is another imaginary sphere that we use for reference so we can understand where things are at. And I'm not going to go into detail of that, but that's a very, very deep subject. And there's a lot of people that argue on both sides of that, and I don't participate. So just know that. I won't participate in arguments on that, on anything really. I just don't do it. It doesn't get us anywhere when we're getting mad and mean on each other. Nothing's being pushed forward on either side when we do those kinds of things. But anyway, what I am going to do, real quick guys, I am going to show you a couple things here. Oops, wrong one. So give me just 1 second. I need to bring something in here, okay? Well, I don't want you guys to have to look at, we'll just run this one while I'm bringing this up. That's the sun right now. It's the most recent, okay? What I do want to show you is, if you guys need to go check out Marfugel's show last night, okay? Because Rip had the comet and sent pics into Dex, and they showed the comet from Rip's location. But I showed you guys this Aurora photography yesterday. This one was a Kayla is who sent this to me, I believe. Okay? I want to make sure that I don't miss out on saying that, because that's one of the best Aurora photography that I've seen during this whole event. Okay, but I also want to show you this, and I've shown you guys this one before. This was a couple weeks ago. This is actually a time lapse from Gary Mustard. Okay, and what Gary has done here, he was talking about Aurora moving kind of the wrong direction, I guess. And I don't know if there's a right or wrong direction Aurora has to move, but I could see that, right? But, I don't know, I'm not sure how unusual it is to see those things, right? See those kinds of things. And I want you guys to look at something here, because something's been bothering me. And I might not even say this. Can you guys see this? Okay? I would challenge you guys to find that signature. This is a artifact of the lens, guys. Gary will tell you the same thing. Whenever you see these like circles like that, it's very faint, right? It's always going to be in the middle of the picture, or close to it. And the reason is that's the center of the lens. So I don't understand why we keep going off on this is something different than that. Because I can recreate this taking a picture inside of my house. I'm serious. This is a camera thing. So I just want to make sure that you guys know my opinion on that, and that's where I'm going to leave it. I'm not going to go into any more detail because I don't care, right? Because I won't argue with people on that. Until somebody can tell me exactly what that is with some good hard science. If they think that that's not a camera thing, then, I'm not going to have anything for it. You're going to have to show me 100% proof with math and everything else that this is not a camera anomaly. It is. It's a camera anomaly, guys. Just my opinion, right? You see how much it showed there? Right? Notice that thing is not moving, but everything else is. Wouldn't you think that if that was something that was there, it would move with everything? Just saying, because that is what I'm not sure exactly how much time is there. If Gary's in here, he might be able to tell you how long this time lapse was, but that's a significant amount of time. Probably at least an hour. I mean, heck, he turned the lights on here and then turned them back off. That thing never moved. It stayed where the camera was pointed. He probably had this thing on a tripod. So that's what I'm trying to say. So yeah, Ange, exactly. Light refraction on the concave glass. That's exactly what's called. I'm not going to go into detail what that is. I know exactly what that is. And that's why I'm not, because it causes arguments. But let me say this too. For people that don't know, I 100% understand that can look really, really weird to you. Okay? I'm serious. I used to think that was something different too, till I dove into it and figured out what it was. There's explanations for these things, guys. You just have to go look for them. These are things that don't get explained a whole lot because they're so accepted and known what causes that. Now, you can go get a different camera, and I've seen these in the shape of a triangle because of the lens of the camera that's being taken by has that kind of a shape. So, let's not forget that. You know what I mean? Whatever the simplest answer is, let's go there first instead of trying to go way out here. If you know what I'm saying? But again, I'm open to anything. If somebody wants to show me with some good hard facts that that's not a camera thing, I want to see it. But nobody has ever been able to do that because I really truly think in this case that is what it actually is, guys. So instead of beating a dead horse here, I'm just going to keep moving. But yeah, these are great picks. Okay, so that's just what I'm gonna say right there. That's just awesome right there. Hey, Ricky, the star nova in this month. Yeah, I heard the same thing. I'm not sure exactly where, but yeah. Anyway, I am going to go ahead and pop off, guys. Get over, check out Marfugel. they have some. You'll be able to see Rip's Comet picture and all that stuff, and I'll be showing you guys some more Aurora from you guys, some more Comet pics from you guys. So don't think I'm not going to show it, guys. I'm just not going to show it tonight. So, and sorry for the audio issue yesterday. I felt like a jerk. It was, what, 3 minutes at the beginning of that? Man, I felt like a rookie. But anyway, hey, Ron, thank you for the gifted memberships. Guys, we will be doing a members only here shortly. I'm trying to make time to do it. You know, we're going to get it together and laugh. It's Zoom court. I've got some clips that are ready to go. I'm just trying to find time, and everybody knows I've been kind of on the outs anyway. I've been not feeling the best, so I'm not going to go into that. But yeah, guys, thank you to all my moderators. Love all you guys. Love all my Kool-aid crew. Love everybody watching. Please share, like, all that kind of stuff. Get your butts over to see Axe. Get your butts over to see Rip, Ilea, Trinity, Marfugal. Guys, you go to my awesome channel list. That's what I'll say. Go down there. You'll see the people that I really, really respect and the ones that I would send you to. Okay? Ron, Emergency Management Associates. So, alright, guys. Oh, Mark Pyers, get over there. See him. Hilly, he does a Bible study. Oh, and he just dropped his link in there, too. Sweet. I sent some people your way on Saturday, I think. Pretty sure I did. I know I shouted you out. I'm pretty sure a couple went over that way. Yeah, hey, Axe, good to see you, my brother. Back at you, Callie. Back at you. I love all you guys. All right. God bless. Yahusha saves. And as always, you can drink this Kool-Aid.